will be something very different from what we have heard so far, but not less interesting. And especially for me, because I once worked with monsoon winds in the Arabian Sea back in time, 50 million years ago, so it would be really interesting to listen. Please, go ahead, speak in the microphone, and you also see the presentation there. And little forward, backward. Yeah, and the pointer is there. You can either there or there.
So, very good morning to everyone, and thank you for being here and over the Zoom for my presentation. So, I'm Dipanjan. I'm from Department of Meteorology, and I'm doing my PhD since June 2017. So it's 3 years, more than 3 years now. And today I'll be talking about something that I'm doing currently. So I thought, okay, it's a good opportunity to present my work. And what I'll be talking about today is the tracing of the monsoon precipitation over the South Asian land masses. So basically identifying from where the water is coming to the South Asian land masses and fall down as precipitation. And I'll try to make it as simple as possible. And so you heard a lot about monsoon. So this word monsoon is believed to have originated from the Arabic word mawsam, which means a season. So in good old days, the traders from the Arabian continent have found out there is certain kind of winds that help them to trade, to sail them faster. They can save their fuel consumption, can come to India to do trading, and then they wait for the wind to reverse. So it's happening in winter, and then they come back home safely and much faster way. And later the scientists found that they were correct, and then later they went to discuss that why this is happening. So why this is happening is basically during this northern hemisphere summer, that's June to September months, the northern hemisphere of Earth is tilted more towards the sun. And when it's more tilted, it gets a lot of solar insolation. And when it gets a lot of solar insolation, the land gets heated up much more quickly, because the heat capacity of the land masses is very, very less. So it heats up more quickly than the nearby oceans. And when the air near the surface of the land, it gets heated up, it becomes less dense and moves up. So as this moves up, it creates a kind of low pressure region. Because why it's called a low pressure? Because the air masses goes up, so the push of the air to the surface is very, very less. So air is now higher up. So it creates a kind of void. But it can't be void. So the winds from the relatively high pressure region from the ocean moves towards this low pressure. And when it moves along this pathway, it takes the water vapor from the ocean. And then it reaches the land masses, it condenses out and falls down as precipitation. So this is kind of a broad mechanism how this monsoon works. And this is a kind of visualization you can see. So this purple line is basically, you can see, we call it as an ITCZ, is intertropical convergence zone, and you can see it as a low pressure, I told you, or a cloud band, and you see the month is on the lower part, you can see this May, June. So you see when the sun moves up during the northern hemisphere summer, the precipitation also moves up, the low pressure center also moves up, and then during the summer monsoon, it retreats during the northern hemisphere winter or southern hemisphere summer, it moves down, and then it moves down. So it's also the high pressure and the low pressure system is moving up and down. So this is how basically monsoon works. And the most important question is why it is important to study. We know the mechanism is fine, but why? It's basically the South Asian countries is mostly depend on rainfall for their agriculture, for their economy. So if we provide them with a good monsoonal forecast, they can work on their production strategies, that when to seed, how much amount to seed, and when to cut their crops. Also, the variability of the monsoonal precipitation. So you know that during this June to September, there is a certain amount of rainfall that bound to happen, and that's what we call the mean rainfall. Any variability, any less or more, can give you a droughts or floods. So if you can forecast them accurately, thus you can you can save lives, human lives, and that's the most precious way. And it's not only with the forecasters, it's also with something to do with the government, because they have to do the proper disaster management. You just give them a forecast, but they have to do the proper disaster management. And there were studies that is a disaster management responsible more for the people's life. And the third point I made here is that I came up with a number that summer monsoon precipitation provides approximately 200,000 buckets of water per person in India. And there are a lot of assumptions included. I'm not going into detail about it. But what you can easily say, okay, we know there is a mean rainfall over India. Okay, let's say it's 850 millimeters over India. You know, and we assume that it's uniformly distributed over the surface area. So you multiply the area, you get a volume of water, and then you divide it by the number of percent, you get this number. And one bucket is kind of, I've taken as 10 liters. So it's 200,000 buckets per person. And in Sweden, I was calculating is annually it gets 500 to 800 millimeters. So you do the same thing, you come up with a number of 3 million buckets per person in Sweden. And you can understand that any variabilities from your daily to daily life, it can affect your daily life also. So moving to the next, how we can achieve this. Obviously, we need a very good model, and you know this. You come here, you first open your apps, checks what the forecast today. So the model gives the forecast for precipitations, for temperature and all this. So this model is nothing but the model running with a set of equations, and then it gives you a feeling of, okay, this amount of rainfall will happen, and then you plan your life. Yes, we can achieve through a good model that gives you a forecast. Also, what we can do, we can accurately locate the water mass sources and their pathways from where it is coming. If we know from where it is coming, by studying their variability, we can understand that how much it will affect. I will give you an example. You are living with a friend in an apartment. Okay, every day your friend knows that you start from home, you go a certain pathway, and then you reach your office. Someday he realized that he started from home, but he's not taking the right way. He's taking some other way. So from that way, he can easily say, okay, he's probably not in time, because he knows the shortest possible way, and he deviates from their way. So he knows, so he can predict that, okay, he will be not on time or something. There will be some difference on the final destination. And the third thing is that you can do it with this Eulerian framework and Lagrangian framework. I will describe what is an Eulerian framework. Is basically you go to football matches, to see football matches. You sit on the stadium and watch footballs to move around. The football passes from defenders to midfielders to forwards. So that's the Eulerian way you are viewing it. What is the Lagrangian way? You sit on the football and you travel with the football, and that's how you achieve the Lagrangian way. So you get a lot of other detailed information with the Lagrangian framework. And this is an example I'm giving you. You see this, this is the high pressure area, the orange one, and this blue one is this low pressure area. As I told before in the very beginning, winds are blowing in from high pressure to low pressure, and you have a precipitation minus evaporation map. So negative means you have evaporation domination, and positive means you have precipitation domination. So what you can see, the winds are blowing, the arrow is the wind. So winds are blowing from high pressure to low pressure, and you have an evaporation in the southern Indian Ocean over, this is called Arabian Sea. So you can have an idea, okay, probably the winds carrying the moisture from this region and then falling down as a precipitation here. But what you can't get is the quantification. How much? How much is this evaporation is responsible for precipitation over the Indian landmass? And you can achieve this through Lagrangian framework. So what I have done, this is I defined as a South Asian land masses, not everything. Like I defined this is a basin, land or local. I defined. I started my Lagrangian trajectories from there, and trace it backwards to see from where it comes. And I divided into 4 basins, is called Arabian Sea, Bay of Bengal, and Central and South Indian Ocean. And I try to quantify that how much amount of water masses is coming from this region to this region. And I'm not going into detail about the modeling or something, but what I want to convey you here is that take a note about this model, track mass. So you can use this model to track the atmospheric water mass. And I'm emphasizing here, it's water mass, I'm not tracing any air here. This is something related, this is something else, but just want to convey you, there is a model called track mass that you can use to trace the atmospheric water mass, like this kind of studies. So this is the result what I got. I ran for 10 years, for June to September, that's the summer monsoon month. And I started, as I showed, from these land masses, and then trace it backwards to sea. And you can see there's a big green blob over the land mass only. So certain amount of contribution is from the land only. So evaporation from the land falling down as precipitation on the land only. But there is evaporation coming from Central and South Indian Ocean. You have from the Arabian Sea, a little bit in June over the Bay of Bengal, from the Bay of Bengal also. But, and you can see this signal is getting stronger in July and August because it's the peak monsoon months. So the moisture is more coming from Central and South and Arabian Sea, and then falling down as precipitation here. But here also you are missing some stuff, you can't quantify how much. So I take an individual trajectories and counted. So this is the chart I came up with. And you can see in June and September, the green line is more. That means the contribution from the land is more, is around near close to 39–40% contributing. And then in July and September, August, that is the peak monsoon months, the Central and South Indian Oceans giving you the most rainfall contribution. And the contribution from Bay of Bengal is very, very less. And I will end up here and leave with you with this conclusion that the Central and South Indian Ocean is dominating most of the time, and then it's followed by the land and Arabian Sea and Bay of Bengal. And if you have any other questions, like more detail about the modeling and all this, you can contact me. Thank you. Thank you for your questions. Thank you.
Thank you very much. Very interesting. I like monsoon winds. I was working with benthic forms, but tracking them back in time, see when the monsoon started in that area. That was about 9.5 million years ago. But does anyone have a question?
One question with rising temperatures and then the ability to have more water vapor in the air. Do you expect the flooding to be worse, or will it kind of cancel itself out because the air can hold more water?
That's a nice question. A lot of studies have been done on that, and what people say is that yes, the extremes will be more intense because of the greenhouse gas emissions. That's obviously human-induced ones. And yes, and there is, but the water vapor will increase because what we call is a Clausius-Clapeyron equation. So if you increase 1 degree centigrade, and then you have the water, the atmosphere can hold 70% more moisture. So you can expect the more flooding and more extremes. The dry regions will get drier, and wet regions will get wet, and that's a common concept. I think in Iceland, but they also mentioned it with a very highly likely event. Yeah.
I actually don't have a question because my question was just asked. I want to ask exactly the same thing, but I just still, as the microphone was passing, want to thank you for the beautiful analogy of Lagrangian in your area. That was superb. That makes it much easier to understand.
Thank you, much appreciated. Thank you.
Deepan. I have a question about how closed this kind of cell is. Is there the sources you've tracked here? How much of a proportion of the total rainfall in these basins is it? And if it's as closed, are there other monsoon systems that are kind of a closed cell like this?
I can't get your question. Can you speak louder? I can't.
Yeah. So, how much of the total basin rainfall is from these sources versus from other sources? Because you have there's zonal winds near the equator and so.
Yeah, that's a nice question. So you can see it adds up until up to, you can say up to 70%. If you add all the sources, it can goes up to like 70 to 80%. So it gives you most of them, 20% from other sources, and very heterogeneous. It's not homogeneous. Some part is a little bit from the Mediterranean, probably something from the Atlantic also, something. It's very, very less. The most of it is determined by these 4 basins. No. Thank you.
Thank you very much. So, this was the sort of end of the first session. We'll now